on distribution of frequencies.
Okay, thanks everyone. I want to thank the organizers for inviting me to this workshop. It's been really interesting. This is joint work with Xi, Zhengyang, Ying, and Jinyu, and it's going to have a slightly different flavor from a lot of the talks we've seen so far, though there will be a little bit of lower bounds in it. It's really a talk about Boolean function property testing. So what is Boolean function property testing? It is at least a talk about Boolean functions. Just to remind everybody, a property of Boolean functions is just another word for a class of Boolean functions. And in Boolean function property testing, the types of classes we typically consider are very similar to the types of classes we're concerned with in computational complexity. Classes like low-degree polynomials, half spaces, monotone functions, simple Boolean circuits, so on and so forth. So a testing algorithm, again, this is probably familiar to everyone, I'll keep this quick, is just a randomized algorithm which gets to make black box queries to an unknown Boolean function which is completely arbitrary. Okay, so there's an arbitrary unknown f. The tester can give an x, get back f of x, and the point of the testing algorithm is to eventually output either yes or no, depending on whether or not it thinks the function is in the class or not. Okay, so to make this a little bit more precise, I'll start by talking about the standard property testing model, which is kind of a uniform distribution model, and go from there to the model we really care about, this distribution-free model. So in the uniform distribution setting, a testing algorithm, what is it supposed to do in order to succeed? Well, if the function is sort of inside the green oval, meaning that it's a function in the class, it should output yes with high probability. And if the function is far from every function in the class, it's sort of outside the outer red oval, then it should output no with high probability. So again, these are randomized algorithms, okay? And kind of a crucial thing is that we measure the distance. What do we mean by the distance between f and g? Well, the distance in the standard model is just uniform distribution. What fraction of inputs in the Boolean cube do f and g disagree on? Okay? And as I'm sure we're all familiar, the main concern in this sort of property testing world is information theoretic upper and lower bounds on the number of queries we need to successfully solve this problem. And the gold standard kind of, we want to have algorithms where the query complexity ideally is completely independent of the number of variables. Okay, so just kind of basic background on property testing. So there's been quite a bit of work over the years on algorithms for testing different classes of Boolean functions. I'm not going to go through this list in any kind of detail. The particular class that I'll be talking about is this class of k-juntas. So I'm sure we're all familiar with this. A Boolean function on n variables is a k-junta if it actually depends on only k variables. So there's kind of a hidden subset of k out of the n variables that matter. And you should think of k as being independent of n. It's a constant like 100 or something. Okay? So there's been quite a bit of work over the years on testing k-juntas. It's probably the best studied class in Boolean function property testing, and it kind of is hidden even in some of the results up here. So results on half spaces, this last bullet, these are based heavily on k-junta testing algorithms. Okay, so we'd like to understand the complexity of this problem. And in fact, we do understand the complexity of k-junta testing very well. So if we consider general algorithms, which are allowed to be adaptive, basically k over epsilon, or at least for constant epsilon, more or less a linear in k number of queries is necessary and sufficient for doing this k-junta problem. Okay, and even if we want to sort of slice the onion finer and think about non-adaptive algorithms, we also understand there, with quite a bit of precision, the number of queries we need in order for non-adaptive algorithms to solve this testing problem. This is joint work with a number of people in the audience, Eric and Liang, among others. So we seem to know everything. What does this talk about? Well, k-junta testing is well understood in the standard model, okay, but you can extend sort of the natural standard property testing model, and I think there's good reason for thinking about kind of distribution-free extensions to the standard property testing model. So I don't want to spend too much time on this motivation, but I think you could really think of junta testing as potentially a useful kind of data analysis primitive. I don't know if anybody wandered in from the other semester at Simon's. If you did, you can run out screaming anytime you like, but if in some sense, I think of junta like a function as a junta if it's a phenomenon that depends on like a very small number of causes. You might want to know in the real world, is this phenomenon, is it complex? Does it have many causes or few causes? But if you want to sort of put the standard junta testing model into a real world data analysis scenario, it only matches up well if your data is sort of uniform over the Boolean hypercube, because this is how we think of distance. And probably in most settings, real world data isn't distributed like this. Okay, so it's natural to hope for a more general notion where we aren't tied to the uniform distribution. And that's exactly this distribution-free junta testing model. So let me contrast this distribution-free model with the standard model. It's quite similar, but there are two kind of essential differences. The key difference is there's now an unknown distribution D, completely arbitrary. The testing algorithm doesn't know it. It could be anything. Okay, and that's the distribution with respect to which we think about as kind of a distance measure for Boolean functions. We now look for the distance between f and g. What is the mass that's on the symmetric difference with respect to that distribution? Okay, so this is sort of our notion of an interesting distribution now. And of course, if that's the interesting distribution, we'd better somehow let the testing algorithm get some information about it. So as before, the tester can make black box queries. It has a black box oracle. But we also assume that the tester can make draws from this distribution. So it can push a button and get a sample from this distribution. And then, of course, it can query the function on this point if it's interested, and so on and so forth. So it has some access to this unknown arbitrary distribution. And now it's supposed to tell whether f is in the class versus epsilon far from the class with respect to this distribution. Does the framework make sense?
The drawings are free. Getting independent draws doesn't cost you.
No, if you could get arbitrarily, everything costs 1 penny, or I guess in today's world $1 for each type of query. Yeah. Okay, so just a little bit of background. People have studied distribution-free testing for kind of a modest number of classes of functions. And the takeaway message, I don't want to spend too much time on this, is that for the classes that were sort of studied to date, distribution-free testing looks a lot harder than standard testing. So for various classes where we have a kind of gold standard query complexity completely independent of n in the uniform distribution setting, the query complexities were known to be polynomial in n in the distribution-free setting, and you can also have these kind of exponential gaps as for monotone functions and so on. Notice that distribution-free testing is certainly at least as hard as standard testing, because one possibility is that the unknown distribution is just the uniform distribution. Okay? So kind of the goal with which we went into this work was to understand K-Junta testing, right? This Junta testing problem, which has been so well studied in the uniform case. Well, what happens in the distribution-free model? Are Juntas easy to test? Are they hard to test? And we have more or less a complete answer. So as I'll tell you, we showed that Junta testing for non-adaptive algorithms is sort of hard, but it turns out to be quite easy. We were surprised by how easy it is for adaptive algorithms. They're very efficient distribution-free adaptive Junta testers. So let me tell you about the results in a bit more detail. This is not a new result. Just as kind of a simple combination of previously known results, it can be shown that the class of K-Juntas can be tested in this distribution-free setting by a non-adaptive algorithm. Okay, but the query complexity is exponential in k, 2 to the k. So on the one hand, great. It's independent of n. That's kind of an important thing to know. On the other hand, it's exponential in k, and we'd like to have a more refined understanding. Right? Do we really need this exponential in k or no? So the first result, there is a lower bound in this talk, is a lower bound for non-adaptive distribution-free testers. If you want to test even to some very coarse, yeah.
You have a line there before this new theorem explaining the old theorem.
Oh, you take the fact that Juntas have self-correctors, you take the fact that there's a uniform distribution tester for Juntas, a two-line argument gives you this theorem. So, yeah. Good. So the takeaway message from the bottom line, which is a new result, is that the simple kind of combination of these previous results is essentially best possible if you want to be non-adaptive. Non-adaptive distribution-free testers need an exponential in k number of queries. Yeah, Clement?
That one-line argument for the testing, does it go through if like somebody came up with a tolerant tester or distance approximation for Junta? Would that give the distribution free?
Good question. I'd have to think about it. Yeah, I'm not sure.
So when you say non-adaptive, so...
Yeah, I'll explain exactly what I mean by non-adaptive a little later. Yeah. Okay. So that's the lower bound for non-adaptive algorithms. The upper bound says that, hey, adaptivity actually buys you an exponential improvement. So it turns out that there's an adaptive tester. It's even one-sided. It only makes false positive, I guess, mistakes, or false negative mistakes. I can never remember which is which. For K-Juntas, which is almost as efficient as the distribution-free case, in the uniform case. In the uniform case, we know k over epsilon is possible. In distribution-free, we can do k squared over epsilon. Okay, so pretty close. And this is, again, kind of dissimilar to these other classes we looked at earlier, where we had either constant versus polynomial in n, or poly n versus exponential in n. Here it's a polynomial relationship between distribution-free and uniform distribution query complexities. Okay, so that's it. Thank you very much. No, I'll go a little longer. Yeah.
Is there any type of VC type dimension, like a property that captures this?
Yeah, that's a great question. I have never seen anything like that, and I don't think it's likely that there is something like that, because like with property testing, it's not the case that if I have this class and then I have a larger class, that the larger class is necessarily easier or harder to test than the smaller class. As you grow a class, it can get easier than harder than easier than harder. Like the empty class is easy to test. The class of all functions is easy to test. Things go up and down in the middle in different ways. So I don't know of any kind of dimension like that capturing it. Yeah. OK, yeah. So in the rest of the talk, I do have some time left. I'll say a little bit to give you kind of an intuition for where the lower bound comes from. But I'll probably spend most of the time on the upper bound, sketching some of the ideas behind how we can get a poly K-query algorithm. OK, so let me tell you a little bit about the lower bound. Most of what I want to accomplish here is just to tell you the construction, because I think given the construction, you sort of look at it and you say, yeah, probably there's a lower bound to be proved there. So the technique for proving this non-adaptive testing lower bound is a very standard one. We go through Yau's minimax principle. Now, usually, if you're familiar with this line of work, for the min-max principle, you say, OK, I just have to prove a lower bound over deterministic algorithms. So the job of the guy who's proving the lower bound is to come up with a distribution over yes instances and a distribution over no instances. That's also our job. But in this framework, since it's this distribution-free setup, the yes instances, this yes distribution is going to be a distribution over 0, 1 to the n, comma, Boolean function pairs. Right? That's what this distribution ds is over, and dno is also over distribution function pairs. Right? And we have to show that algorithms that make 2 to the k over 3 many queries, deterministic algorithms, can't tell whether the distribution function pair was a yes guy or a no guy. Okay? So that's kind of our job. OK, so let me try to tell you about this yes case and this no case. The yes distribution over distribution function pairs. I'll start by telling you about the distribution, which is extremely simple. To generate the distribution part of the distribution function pair drawn from D yes, I uniformly randomly pick 2 to the k log n points, somewhat more than 2 to the k points. Okay? And I make my distribution uniform over those points. So this is just a bunch of black dots here, these 2 to the k log n points. Okay? The function part of the distribution function pair is exactly what you'd expect. You pick a random k junta. So you choose k variables uniformly at random. Given the identity of those k variables, right, there's 2 to the k possible settings for those variables. The picture is supposed to illustrate kind of the different possible settings of the relevant variables. We think of these as sections into which the Boolean cube has been chopped up. And we just pick a random function over those. So we just color each section, toss a coin, and color it black or white. Okay? So this is the distribution function case in the distribution function pair in the yes case. It's obvious that these are all yes functions. They're all k juntas by construction. Okay? For the no case, it's supposed to look similar, but it's different in crucial ways. So the distribution is exactly the same. We pick 2 to the k log n random points. The distribution is uniform over those points. Okay? The function is sort of where the action is happening. We do the same thing as before. We pick k variables at random. We color the sections at random. But there's a twist. Within each section, in a Hamming ball around the point where the probability distribution is supported, we toss a fresh coin. And we color all those points according to the fresh coin toss. Okay, so again, like these are big Hamming balls. The radius is 0.4 n, let's say. But we only sort of have this Hamming ball restricted to this section. All the Hamming balls are just restricted section by section by section. Okay? So this is the no construction. And I'm not going to give a proof, but I do need to at least explain to Emanuele and to everyone else what is even meant by a non-adaptive algorithm. Okay, so what is a non-adaptive algorithm in this setting? Well, the fair way to define it is that first the algorithm gets to press the distribution button 2 to the k over 3 times. Okay, it sees the points that came from the distribution. Then it gets to make 2 to the k over 3 again, let's say non-adaptive queries. So these queries can depend on what it saw when it made its draws from the distribution, but it can't choose the third query point based on the answers that it was given in response to the first and second query points. Okay, so does this explain what's meant by non-adaptive? Good. Okay. Good. So that's a non-adaptive algorithm. We kind of have to show that the data we get in the first part doesn't help. These 2 to the k over 3 many samples aren't informative, and the 2 to the k over 3 many non-adaptive queries also don't help us. So it's kind of easy to see that the samples are useless, right? What are you going to see in the yes case when you make 2 to the k over 3 many draws from the distribution? Well, birthday paradox. You'll see a different point in every section with high probability, and that's exactly what you'll see in the no case. So I don't know if you can see. These are like red dots spread across the sections, red dots spread across the section, and the color of each dot is independent, uniform, random. The samples, they just look exactly the same. Okay? So that was no good. What about the queries? This is, of course, the more interesting part. Maybe non-adaptive queries, somehow I can figure something out. Okay, so what can non-adaptive queries do? Well, they can't do much. I'm not going to prove that, but let me just try to give some intuition in this one slide. Intuitively, if you want to tell that you're in the no case as opposed to the yes case, what you need to do is you need to be able to come up with two inputs, 2 points, could be anywhere in the section, that are labeled differently. If you don't succeed in doing that, then you're really seeing the same thing in the yes case and the no case, right? This is the way in which the yes case and the no case differ. Okay, so how could you try to come up with 2 points in the same section that are labeled differently? Well, probably you're going to start with one of your sample points, which is like this red point here. And what are you going to do? Very much not a proof, but intuitively, I think the only thing you can do is you can flip some number of bits, go away from this point. And it's sort of a lose-lose situation. Suppose you flip a lot of coordinates. Suppose you flip more than n over k many coordinates, right? Well, by flipping, 1 over k fraction of coordinates, you're going to wander out of the section probably. And so that's not doing you any good. If you flip a lot more than n over k many coordinates, you're probably going to end up at like this green point or this blue point. You'll wander out of the section, and you won't be accomplishing your goal of finding a differently colored point in the same section. On the other hand, if you don't flip too many bits, if you flip less than n over k bits, maybe you will stay in the same section, but remember, these Hamming balls are of radius 0.4 n. They're really big. So you didn't flip enough bits to get out of the Hamming ball. You're just going to see another point of the same color because you're in the same spot. Okay? So this is the intuition which underlies the lower bound. You can make it precise and prove a 2 to the k over 3 lower bound for non-adaptive algorithms. Does it make sense at some intuitive level? Good. Okay. Good. So I guess I still have some time left. In the rest of the talk, I'll say a little bit about the adaptive algorithm. So again, to remind you, this is going to be an algorithm. We know it has to be adaptive by the lower bound we've just seen, which will succeed in solving this epsilon testing problem with a polynomial number of queries, basically k squared many queries. Okay. So we somehow have to use adaptivity. How are we going to do it? What's an adaptive algorithm? Well, the all-time great adaptive algorithm, in my mind, is probably binary search, right? You see what happened, you choose your next step, so on and so forth. And indeed, this uniform distribution Junta tester of Eric Blaise, the kind of the gold standard for the best query complexity, uses binary search in a very simple, but very conceptually very simple, but very, very effective way. So let me sketch for you a simplified version of Eric's uniform distribution testing algorithm. Remember, the real tester, the result of this paper is a k over epsilon query algorithm, independent of n. But what I want to sketch for you is a much worse algorithm, an algorithm which also has a log n factor in the query complexity. Okay, and it's not too hard to imagine how this would go. It's probably going to do some kind of binary search. That's exactly what it does. Essentially, this simplified version of the algorithm that I'll tell you about, I think of it as the way it works is it repeats, let's say 100k over epsilon many attempts to find a new relevant variable. Okay, if it succeeds in finding a new relevant variable k plus 1 times, then it knows that it's not dealing with a Junta because it's found k plus 1 many relevant variables. On the other hand, intuitively, if I made 100k over epsilon many attempts to find k plus 1 relevant variables and I didn't succeed in finding them, it hopefully seems intuitive that probably the function is epsilon close to not having k plus 1 relevant variables to being a k Junta. Okay, so this is exactly how we should think of the algorithm as working. It repeatedly tries to grow by 1 a set of variables that are known to be relevant. How does it grow by 1 a set of known to be relevant variables? Well, it does it in a very natural way. You pick a random point x, okay, and you re-randomize the coordinates which are the ones in question, the ones outside this set of known to be relevant variables, to get a new point y. Right? You know you didn't change any of the relevant variables because you only re-randomized the coordinates outside the set R of relevant variables, and you query these 2 points. Maybe they disagree. If they disagree, you're in luck. Do binary search and find a new relevant coordinate. Okay? So I felt compelled to add this next slide. I think we've all seen binary search, so I don't know that there's a great deal of point to it, but maybe just as kind of an illustration, for the set of variables that we know to be relevant so far are 1, 2, and 3. You draw your string x, and then when you're drawing your next string y, you freeze those coordinates, you re-randomize all the other coordinates. You hope that actually the function has different values on those 2 inputs, and if so, you do the binary search. We all know how to do binary search, right? And it's going to take, of course, log n queries to find the relevant variable with that binary search. Okay? So hopefully it's clear why this algorithm has a query complexity like k log n, and we sort of do the whole thing, k over epsilon many times in our attempt, so that's the overall query complexity for Blaise algorithm.
What
Okay?
if the Junta is an end?
Excuse me?
What if the Junta is an end of k variables? So then you would find the difference only with...
Then if epsilon is less than 1 over 2 to the k, it works. If it doesn't, if it's
so
not, then it's off the hook. So yeah. Question, yeah?
But in the distribution-free setting, it seems very difficult to fix those first k bits and make queries that are relevant.
Yeah, I didn't say this works in the distribution-free setting. This is the warm-up to the uniform distribution algorithm. So
That's
yeah,
what you have to overcome.
that's what we have to overcome. Yeah, yeah, I'll hopefully get there. Right. So just a quick word, because it is relevant for our work as well. How does Blay do better than this? Why does he not have a log n in his query complexity? Well, he works with blocks of variables instead of single variables. You sort of have to never get your hands dirty and even identify a single variable. You need log n bits of information to identify one variable. You don't want to make log n queries. So he randomly partitions the variables into blocks, does binary search sort of block-wise instead of variable-wise, and is able to put it all together and get a query complexity independent of n. His analysis heavily goes through this kind of Efron-Stein or Fourier decomposition. It crucially relies on product space structure. And his algorithm works for any product distribution, in fact. But it's, like Russell is suggesting, it's unclear. It was unclear to us for quite a while what to do in the distribution-free setting. Okay? So that's kind of a challenge. Turns out that if you're willing to lower your standards, which we thought we were for some time, you can get away with a very, very simple variant of the algorithm I just showed you. If you're willing to have a log n in your query complexity, okay, then really a one-line, a 5-word change of the simple algorithm works. And the analysis is quite simple. Okay? The only change is that you do exactly the way you did it before. It's just that you draw that first string x from the distribution D instead of from the uniform distribution, which is very natural. Okay? It wouldn't really make sense to re-randomize y according to distribution D. Right, to try to find that other string. What you do for y is you uniformly, again, just as before, this is highlighted in red because it's important for what's coming up, but the red italics part is exactly the same as the uniform algorithm. The change is that you draw x from distribution D, and then you do everything as before. But this is the key thing. You have to be able to uniformly re-randomize all the coordinates outside that set of relevant variables. Okay? And if you can do that, then there's a kind of a simple structural result, and it just goes through. Yeah?
So here, it's kind of important that it's not a tolerant, that you're not doing like a distance estimator.
Yeah, you could be misled.
Are distinguishing between things that are actually Juntas and things that are far from Juntas.
Yes, this is future work, which I hope Clement and Eric will do, is to extend our results to the tolerance setting, but none of our results are for that setting. Yeah.
So the number of samples here is just monomer k over epsilon. It's just the number of queries to the function?
For this algorithm, yeah, the number of draws from the distribution, you're right. You only need those for x, so that would be like 100k over epsilon. The queries would be for the y part. Yeah, that's a good point.
This is Fourier also?
This is for what?
Fourier? The lower.
No, the analysis, there's no Fourier in the talk. Yeah. It's a very simple analysis, though. It's not hard at all. Okay, so if we were willing to lower our standards and have this log n dependence, we'd be done. But let's try to do a little bit more. So how are we going to get rid of the log n? Well, intuitively, we kind of know we can never touch a single variable, right? It'll take us log n queries, log n bits of information to learn the name of a variable. That's a road we can't go down. So somehow we have to also be working over blocks, we feel, instead of single variables. Okay, so that's something we want to do. And we saw in the simple algorithm, and the one from the last slide, the key thing is to be able to uniformly re-randomize these coordinates right, outside the set of relevant variables, whatever that set of sort of known to be relevant variables are. But it's weird because we don't know what this set is, certainly. We've never seen, right, I can't even figure out the name of a single variable unless I make log n queries. So it feels a little bit like a chicken and egg thing. How am I going to re-randomize these coordinates outside that set without knowing what is in that set? Okay? So we'll see that that's exactly what we are able to do, and being able to do that sort of is the key to the result. Let me tell you a little bit about the setup for the algorithm. Kind of, once you have in mind what you want to sort of maintain, it's not that bad. So the algorithm, we're going to think of it as maintaining a list of relevant blocks, so disjoint blocks. This is like the variables 1 through n. This block B1 is over here. This other block B2 is over here, so on and so forth. Okay, so we're going to maintain these blocks. For each block, we're going to keep 2 strings, an x string and a y string. And these are kind of the strings which witness the fact that the block has a relevant variable. So if you look at x1 and y1, they match everywhere except on this block. In this block, they're different. Okay? So there's like a common assignment outside the block. I call that wi for xi and yi. Okay? And f of x is different from f of y. So this kind of the existence of these strings x and y, where the function differs and they differ only within this block, tells me there's a relevant variable in that block. Okay? And kind of a key assumption, which took us a long time to get to, is that we want to assume, we'll see in a minute how it makes our life much easier to assume that for each one of these blocks, if I restrict the function in kind of the correct way outside the block and reduce it to just a function over the variables in this block, let me for the moment assume that that function is actually close to a one junta, okay, to like, just a single literal function somewhere, one of these literals in here. So the picture is supposed to capture this, that, I don't know if you can see, within this block I have like one bold-faced variable because fixing all the other variables, as according to x2 and y2, it's a one junta here on this bit. Fixing all the other variables outside here, it's a one junta on this bold bit. This is what we want to assume that we've got so far. Okay, some blocks and this kind of x and y info, and it's like a junta, a one junta over b1, a one junta over b2. So far so good? Okay, good. Good. Great. So this is just repeating what I just said, that this is what the algorithm holds on to. Now let me define this set R, this set of sort of known to be relevant variables. I don't know what that set is, but the right way to think of this set is it's that collection of junta variables. So it's like these bold variables from the last slide. This would be one of the variables, whatever coordinate this is. This would be another variable, whatever coordinate this is, and so on. That's like the set of relevant variables, okay? The key to the success of our algorithm is the fact that actually we can uniformly re-randomize the coordinates outside that set, even though we don't know what that set of relevant variables is. Okay, so in the next slide I'll show you how we do that, and then hopefully it'll become clear how the whole thing works. So what do I want to argue? I want to argue that I don't know what this v1 is, this one junta variable in this block. I don't know what this v2 is, this one junta variable in this block, but I can still come up with a uniform random subset of the complement of the set v1 and v2. A uniform random subset of the complement is the same thing as being able to re-randomize the variables outside that set. So how do I do it? Well, let me attack it one block at a time. For the first block, I'll randomly split the block into two pieces, okay? And I just need to be able to tell now which block is the relevant variable in. And that's easy to do, right? The function restricted to this block is basically a one junta, so I flip this half, I flip the complement, I see which time it changed. Okay? So I can tell which piece v1 is in. When I split b1 into two pieces, I can tell which piece v2 is in. And if I just put together sort of this information along with a uniform random subset of the rest of the stuff, I'll get a uniform random subset of everything but v1 and v2. Right? So why? Well, if I take a uniform random subset of everything that's not in the block, it's a random subset of the white stuff. Let's think about the first block. If I randomly split b1 into two pieces, and I can figure out which of those pieces doesn't have v1, and I take it, well, that's exactly a uniform random subset of everything in block 1 except for variable 1. Okay? You have the same thing for block 2, union everything together, and you've got exactly a uniform random subset of everything but v1 and v2. Okay? So we're able to do this key step of re-randomizing uniformly all the coordinates outside the set of relevant variables, even though we don't know what that set is. So I owe you something, right? We made this assumption, which was that each restricted function, each sort of way of restricting the function to block 1 to block 2 is close to a one junta, right? How can I enforce this assumption? How do I actually, end up in a situation where the function is close to a one junta over block 1, close to a one junta over block 2, so on and so forth? Well, we use the one junta uniform distribution testing algorithm. Right, I just restrict all the variables outside the block according to the fixed setting shared by x and y, and I run the uniform distribution one junta tester on the block. What can happen? One of two things can happen. Maybe the tester tells me, congratulations, you are a one junta over that block. If that happens, that's great. Right, that's what I wanted. The other possibility is that the uniform distribution one junta tester rejects. It says, you're not close to a one junta over that block. But if you look at the way the uniform distribution one junta tester works, when it rejects, it kind of rejects with a certificate. It rejects because it found two relevant blocks. It sort of came up with two blocks where it knows there's a relevant variable in each one. So in this case, the output of the one junta tester lets us make progress. It splits what was previously a block that I knew had one relevant variable into two blocks, each of which has one relevant variable. So I've made progress toward my sort of overall goal of coming up with k+1 blocks, each of which has a relevant variable. If I can do that, I know it's not a one junta, it's not a k junta, and I'm done. Okay, so the algorithm on the next slide is probably not worth going over in detail. You just combine these sort of intuitions in the obvious way, and you're able to get the overall tester. So I just want to close by talking about a little bit of possible directions that I think would be interesting for future work. I'm just reminding you of the results here. It's this algorithm that we just sketched with a poly k over epsilon query complexity using this binary search idea and the lower bound for non-adaptive algorithms. In terms of future work, one goal is obviously it would be nice to get sharp bound. So currently we're a little bit off between distribution-free and uniform distribution. In the uniform distribution case, we have basically k over epsilon query algorithms, and here for arbitrary distributions, we seem to need k squared instead of k query. So it'd be nice to close that gap. Maybe a more interesting goal is to try to extend the result in the sorts of ways that you guys addressed already with questions. It would be nice to understand something about whether we can make this distribution-free tester tolerant. We don't really know very much about making uniform distribution testers tolerant. We don't know as much as we would like. There are other variants of testing models if you're sort of motivated by making it potentially practically useful, such as active testing, sample-based testing, and so on. So some directions for future work. That's it. Thank you. Sasha, yeah?
Yeah, so on the previous slide, we had T is the number of blocks. So is it roughly K or?
T is the number of blocks. So the algorithm builds this up. Initially, starts with like, yeah, I guess maybe the whole set of n variables is one block or something. It builds it as it goes. If it ever reaches k plus 1, that's when it stops and says you're not a k junta. And if it tries 100 k over epsilon many times to build it up to k plus 1, and it didn't get there within 100 k over epsilon tries, then it says no, you're not a k junta. Yeah.
So one more question. So your argument for non-adaptive adversaries does it basically imply that black box query access is useless or something? What's the VC dimension of k juntas?
The VC dimension of k juntas, I guess, is I think it's just k. It's just k.
It's probably 2 to the k at least.
It's embarrassing. I'm on tape. I'm teaching a learning theory course this semester. I'm probably going to give this as a homework problem next week or something. I think it's k, right?
No, I think it's 2 to the k at least, right?
You're probably right. Yeah, 2 to the k.
So that means that even without, and it's at most, I don't know.
But the VC dimension is, as far as I know, kind of coming back to Amir's question, I don't know that it has any relevance for uniform distribution property testing, for distribution-free property testing. It's a learning theoretic parameter. It tells us about the query complexity or the sample complexity of learning, but I don't think it...
Doesn't it just say that for every distribution, even without black box access, you can learn it in VC dimension?
No. Yeah, I've had the same dreams about trying to sort of connect these things, but the VC dimension, I mean, one way to see it is the VC dimension has no notion of distribution tied to it. Like you could have a concept class which has large VC dimension, but it's because of a very small set of examples, which really have nothing to do with whether the function is globally like in the class or far from the class, right? So I don't think there's a connection that can be made there. Yeah.
Sorry, you might have already said it, but if the one junta tester rejects, this just means that the block, this gives you a certificate that the block is close, or gives you a certificate that there's 2 blocks that are far away from one junta under the uniform distribution.
Yes,
right?
Exactly.
So how do you convert this to progress in the distribution thing?
As long as your function is not a k junta, distribution-free tester can reject safely, right?
Okay.
So yeah, so that's good enough evidence even for the distance with respect to d. If you know that it's not a one junta, if you know that the function is not a k junta, you can reject and you're off the hook.
Okay.
Yes, this is not an obvious fact that Lay's algorithm gives you this certificate, but take my word for it, it does. Yeah. Hold on. Yeah.
So for the lower bound, it really relies on the fact that it's non-adaptive, and the upper bound, like what number of like adaptive rounds do you use? Like I guess it's like in the uniform case, just like you do like a full binary search. There is no way to say like if I go into like 5 rounds of adaptivity, it goes from 2 to k over 3 to like k to the 17 or something like that.
Yeah, probably instead of k squared over epsilon rounds of adaptivity, I think just k over epsilon, I think would be enough for, if you look at how the algorithm really works, how many rounds of adaptivity. But if someone asked me that question, I would say you should ask Clement that question. He's the guy who would know this kind of thing. So yeah, you could look at the algorithm and determine, I think it would be polynomial in K, certainly. Yeah.
Other questions?